Questions? That's true.
Yeah, so number 8, stresses and beams.
That's a different class.
Oh, yeah.
Nick, we're losing you.
Yeah, I've already been lost.
Okay. Okay, so let's go. Yes. Okay. Can I see it?
I guess it's number 9.
Yeah. Good. Yeah, number 9.
I figured it out. It was pretty cool. It was pretty badass. And the master about it. And I was like, oh, this is pretty cool.
Can we do that thing where you guys don't talk and I talk? Okay, great. That's how I would like to do it. So this one, we have a bar this way and a pin joint connecting to a bar this way. Let's see. And at that point, this connects to the bottom of a disc. It looks like maybe the disc is connected to the beam at another point, but it's not supposed to be. It wouldn't move if it was. Yeah. And then this is connected to the ground at the center point. But it sort of looks in the picture like it's possible that this pin connects to the disc, but it doesn't. Yeah, so the disc is fixed to the ground at its center. Yes, that's right. Offset.
That was too hard. I just kind of relevant. It's kind of like a red herring. Yeah.
Did I give a solution to this? So that would just come in at where it would come in. So when you do your constraint, let me label these joints. So I call that point A. So I guess I'll call this B, C, D. And so the constraint at D would say that, so the acceleration of this point according to the perpendicular, this member, you'd say that's the acceleration of the center plus watermelon equation for the end. And then for the disk, you'd be comparing that not to the acceleration at the outer radius, but the acceleration 5 centimeters from the outside.
Oh, that's what you were saying by that. I was taking it, the way the picture looks, it looks like the center of the disc is opposite.
Oh, no, it's not. It does look like that, now that you mention it. But no, that's just saying that pin isn't connected at the end of the disc, at the edge of the disc. It's 5 centimeters in.
Sorry. If we use the radius, then it's not. Right.
Right. Right. Right. If you did it that way, I don't think I have to tell you, don't do it over again, don't correct it, that's fine with me. But just understand how that would come into the problem, Okay, so, these take forever, so I'm not going to go through this whole problem, but were there any specific parts? Oh, okay. Okay. Notice that this is exactly the same problem as if this wasn't a disk at all. And this was just like another beam like that connected at the center. I mean, I guess this, you'd have to fiddle with the dimensions to make the moment of inertia be the same. But other than that, the fact that that's a disk can, sometimes you can get thrown off about, the circular motion or whatever, but all that matters there is the motion of that point around the center of the disk. Any other homework questions right now? Yep. Yeah, that seems funny because the ground is the fourth bar. So there do need to be four rigid structures. That is why it's called a 4-bar linkage, but a lot of times the ground is one of them. Yes. Yep. Okay, so last time, I introduced the idea of polar coordinates. And the idea is if you have this implied reference frame, sometimes for certain types of motion, it's easier to describe the motion of a particle in terms of its distance from that implied origin and the angle from that implied x-axis to the line that the particle is on. So this would be your angle theta. This distance would be r. And the polar coordinates are r theta. But even though that's how you specify the position of an object, that's not a position vector. So in order to define position, velocity, and acceleration vectors, you choose a coordinate system like this, where this is the ER axis, this is the E theta axis. And then you also, if you're doing cylindrical coordinates, you also have a Z axis, a K axis coming out of the board towards us. And then in this coordinate system, the position vector is R times that ER unit vector plus 0 times the E theta vector. And so we can just write this vector as R0, where that first ER is the one that's always pointing towards the particle. So if you want to get to the particle, you just had a distance of r in the direction of ER. Okay, so this is your ER component. This is your E theta component. So why would you ever need to, to specify an object's position, we always do it by specifying the r and the theta. Why would we ever need to define the position vector? Well, I guess the answer is when you're doing dynamics, we need this so that we can come up with an expression for an acceleration vector. And we need that acceleration vector so we can use Newton's second law. Okay. So even though this is how you specify an object's location, we're going to start with this and work towards velocity and acceleration vectors. Okay. So we need this so we can find an acceleration vector to use in Newton's second law. To find the acceleration vector, we're going to use the fact that acceleration is just equal to the second time derivative of the position vector. But this is complicated by the fact that the ER E theta coordinate system changes orientation in time. It's a rotating coordinate system. Yeah, I think that's how people usually refer to that, but just saying, yeah, the coordinate system that's defined by that ER and E theta axis is rotating. No, that's right. Maybe comma is better. Okay, so the velocity vector is the position vector dot. But for a rotating coordinate system, we can think of that as the time derivatives of the components. And so this is the time derivatives of the components of the position vector plus the angular velocity of the coordinate system crossed with the original position vector. Yeah. So our coordinate system is that r theta coordinate system, and that's the one that's rotating. Yep. That's right. So yeah, let's write it like that because with the cross products, we're going to have 3 components. If you're doing cylindrical coordinates, then that z component is going to have a value. All right, well, let's think about what these things are. Our position vector, we figured out above, is r theta. Yeah, because once you've gone R cross in the ER direction, you don't have to go anywhere else. You're already there.
So again, for the component vector, like R0, 0,
Yes, I should have done that. That's right. Yes, exactly. R00. Okay, and what's the capital omega vector? It's 0, 0, and that omega is just the time derivative of theta. And so this is just going to be theta dot. So now I have that omega vector expressed in terms of the polar coordinates. And so the velocity vector is, what's PR dot? Yep, perfect. R dot 0, 0. And then omega is 0, 0 theta dot. And we're crossing that with the original position vector, which is R0, 0. So that's R dot 0, 0 plus 0 R theta dot 0. And so the velocity vector is R dot for ER. For E theta, it's R theta dot, and then 0 for K. So this is polar. Polar means the K value is 0. Cylindrical means it's not 0. And you can also think of this as R dot in the ER direction plus R theta dot in the E theta direction. And the main reason we're doing this is to get to the acceleration vector. The acceleration vector is the time derivative of the velocity vector. And so we can do that two ways. We could use that big ugly expression for the acceleration vector. I'm just going to do it as the time derivative of the velocity vector. So the time derivative of the velocity vector is the velocity vector components dotted. So I'll think of that as VR dot V theta dot 0 plus omega crossed with a velocity vector. Everybody clear on how I'm approaching that? I'm just using, so this is that general result that says this is the way you calculate time derivatives if your coordinate system is rotating. And we're taking a time derivative of the velocity vector. So that means that the acceleration is equal to, this is our velocity vector. So the time derivatives of the components of the velocity vector are just r double dot. And then what's the time derivative of the theta component of the velocity vector? Yep, perfect. Plus r theta double dot. Just need the product rule there. And then we're adding to that the cross product of 0, 0, theta dot with the velocity vector r dot, r theta dot, 0. And so that's equal to r double dot, r dot theta dot plus r theta double dot, 0, plus the cross product. For the x component, we have negative r theta dot squared. Yes, thank you. Okay, so negative r theta dot squared. And then for the y component, we have positive r dot theta dot, and then 0 for the z component. And so our final expression for the acceleration vector, the r component, the first component, is r double dot minus r theta dot squared. Second component, the theta component, is, I'll write it as r theta dot plus 2 r dot theta dot, and then 0 for z. And so the way I did this calculation is first we calculated the velocity vector, and then I took the time derivative of the velocity vector using these new rules that we have for time derivatives in a rotating coordinate system. We also could have just used that messy acceleration expression that we have, given the position vector, and you have to get the same thing. So if you're looking for extra practice, like understanding it, try using that acceleration expression and you get the same thing here. You have something to compare it to. Okay, let's do a concrete problem so you can see how this all works. So let's say you have 50 pounds of concrete. No, just kidding. I am. Yeah, that is, yeah. Okay, so let's say that we have a particle moving in the plane according to, let's say, r is equal to t squared, and theta is equal to 2t. What's the acceleration vector as a function of time in the ER, E theta coordinate system? Well, we know the acceleration vector at any time t is equal to r double dot minus r theta dot squared. And then for the E theta component, r theta double dot, let's see, plus 2 r theta, r dot theta dot. And now I'm just going to, now that we're done with the cross products, I'm just going to leave the E component off of there. Yeah. Yep, exactly. So the acceleration vector, so r double dot is 2. Theta dot is 2. Square that, you get 4. And multiply it by r, so you get minus 4t squared, I think. And then theta double dot is 0, so that first term goes away. R dot times theta dot is 2t times 2, so 4t times another 2. Yep, 8t. Okay, so that's the acceleration as a function of time. How can we check that? What? Yep, so let's do it in, so if you remember when you've done polar coordinates before, I'm sure, you've never spent a lot of time on it, but you've done it time to time in classes or whatever, and maybe you remember that the x component, and now we're talking about this implied light blue coordinate system. The x component is equal to r times the cosine of theta, and the y component is r times the sine of theta. Mm-hmm. Oh, really? Yeah. Huh. That's good. So in the xy coordinate system, the position vector is just equal to r cosine theta, r sine theta. And the xy coordinate system is not rotating. So if the coordinate system's not rotating, to get the velocity vector as a function of time, all we do is take the time derivatives of the components. So that's r dot cosine theta minus r theta dot sine theta. And then for the, let's not do this in general. Sorry about that. Let's plug in the functions that we know right now. what do we know? T squared and 2t. So we have, this is equal to t squared times cosine of 2t, and then t squared times sine of 2t. And so now the velocity vector is 2t times the cosine of 2t minus 2t squared times the sine of 2t. And then for the y component, we have 2t times the sine of 2t plus 2t squared times the cosine of 2t. And then for the acceleration, now we're going to get a whole bunch of terms. 2 times the cosine of 2t minus 4t times the sine of 2t minus 4t times the sine of 2t minus 4t squared times the cosine 2t. Is anyone following closely here, making sure I'm doing this right? Okay. Okay, and then the second component, we have 2 times sine of 2t. It helps changing your voice. Plus 4t times the cosine of 2t plus 4t times the cosine of 2t minus 4t squared times the sine of 2t. Okay, is there any stuff that cancels here? Yes. So we can simplify this a little. So the acceleration is equal to 2 minus 4t squared times the cosine of 2t, cosine of 2t, minus 8t times the sine of 2t. That's the x. That's the x component. And then for the y component, we have 2 minus 4t squared times the sine of 2t plus 8t times the cosine of 2t. Okay, that's not the ugliest thing ever, but it's not that great. Okay, so what might be sort of surprising here? So what we're, like, because you're all relatively stupid, what were you expecting to see when you compared these two things? Okay, No, you're not that stupid. Okay. Like, oh, this paste is delicious. So, yeah, we're expecting everything to come out, and those two should match. Exactly. So we derived expressions. Yeah.
We definitely see similarities because the coefficients are kind of that.
Mm-hmm. Yeah.
The coefficients are that.
When we make it so that the coordinate system is in line with that.
Yes. Yes. That's exactly. So there's one more thing we have to do to compare. And yeah, you're right. The form does look sort of promising, but it's not the same function. The reason it's not the same function is that in general, instant to instant, those two coordinate systems are not lined up. Okay. And so you have to compare, you have to do either a coordinate system transformation so that those coordinate systems are always lined up, or you have to look, at instants where they are lined up. So let's do that. Well, I already said this in words, but those two expressions for the acceleration function aren't the same. But that's just because the ER, E theta, and X, Y coordinate systems aren't aligned for a general time t. General T. That's like Mr. T after he goes into the army. Well, so let's just think of a single instant first and plug values in. What's a T value where they are aligned? Okay, so when T is equal to 0, theta is equal to 0. So let's plug that into these two. I hope that's not just going to give a velocity of 0, is it? That would be such a bummer. Or acceleration. So in polar coordinates, the acceleration function at time equals 0 is equal to 0. And then in the xy coordinate system, it's equal to 2 times cosine of 0, which is 1, times 0, 0, 0. So the acceleration is 2, 0. They match. So that's cool. What if we wanted to come up with a way to make those two things match? What? So what if we wanted to make the functions match for a general time? Yeah, so to make those functions match for general time t, let's think about what we have. So here's our x, y coordinate system. Here's our ER, E theta coordinate system. Where this angle is theta. And let's say that we want to so let's say that we want to take values in our polar coordinate system and transform them into our xy coordinate system. What's the counterclockwise rotation that you have to make to go from here to here? Theta is equal. That's a bad. So to go from this one to this one, it depends which one you're changing into the other one, but you'd have to go clockwise theta. So that angle is going to have to be negative theta. And so your rotation matrix is going to be cosine of negative theta, sine of negative theta, negative sine of negative theta, cosine of negative theta. And then if you use the fact that cosine is an even function, sine is an odd function, this is just cosine theta, negative sine theta, positive sine theta, positive cosine theta. And now we're going to take, so the acceleration in the xy coordinate system is going to be equal to this rotation matrix times the acceleration in the polar coordinate system. I'm not really sure of how people, I think people, that's how I seem to do it, yeah. I've noticed that in reading through my work before. But I don't think, I've never seen like a real uniform way of people to, they just like their voices get a little higher and they like, I don't know. Yeah. We're sort of going off the grid here. When we're talking about like vectors in different, I'm not. No, but I'm not explaining why. Okay, so now we take this and we multiply it by our polar acceleration function. What was that? 2 minus 4t squared. So here we have 2 minus 4t squared, right? And what do we have here? 8t. And so what we get from that multiplication is 2 minus 4t squared times the cosine of theta minus 8t times the sine of theta. And then for the second component, 2 minus 4t squared times the sine of theta plus 8t times the cosine theta. Theta was equal to 2t. And so this is 2 minus 4t squared times cosine of 2t minus 8t times the sine of 2t. Second component, quantity 2 minus 4t squared times sine of 2t plus 8t times the cosine of 2t. It's amazing. I was hoping you would all think that without explicitly saying it.
That you're a wizard.
Yeah. Holy. Isn't that cool?
What swear word is that?
The last one is an actual exclamation point.
Oh.
You'll be looking for that swear word.
Yeah, that's true.
Where do we go points off?
Um,
I like the proof.
yeah. I think this, going through this is helpful because, at least for me, when I first started seeing this stuff, I was kind of like, I think I kind of had it in my head that maybe all of these formulas were just a way to deal with the fact that those coordinate systems are out of alignment. But it's not that. It's dealing with the fact that they're time derivatives of the unit vectors, the axes. That's what all the corrections are for the rotating coordinate systems. Then after that, if your coordinate systems are misaligned, you have to deal with that separately. But there's something deeper going on than just the coordinate systems being misaligned. And first, that's mainly what we have to address. So. Yeah, because then you see that it's 2 steps. In this class, you're never going to have to do that. Well, yeah, you're never going to have to do that rotation matrix step because all these problems are going to be like pre-cooked to have the same alignment of the 2 different coordinate systems. But in general, if you're doing this stuff instant to instant, you would have to do that to compare. Okay, that's all.
So do I stay here to give my quiz then? Too?
No, it'll just be online. You don't have to.
Is it still